Welcome to Chapter 25. In Chapter 25, we're going to talk about free radicals. An example of a free radical is shown here. A free radical has an unpaired electron. You can see bromine radical on the left and methyl radical over here on the right. Here's our outline for this lecture. We're going to start off by doing a brief introduction to homolytic cleavage. What we've done previously in organic chemistry is heterolytic bond cleavage, where we're showing an arrow moving a pair of electrons. And remember that our arrow we used has two barbs. In our mechanisms for homolytic bond cleavage, we're going to use these single-barbed or one-barbed arrows. The one-barbed arrows represent one electron moving rather than a pair of electrons. So in this case, you can imagine in the homolytic bond cleavage, we have one electron going to each side. So if you were to split this up into two parts of the reaction, we have the bond between A and B, and homolytic cleavage means evenly cleaved. So we're cleaving, so that way the blue electron that's half of the bond goes to A over here, and the red electron that's the other half of the bond goes to B. This is how you would draw your mechanism for a homolytic bond cleavage. Okay, let's talk a little bit about homolytic bond dissociation energy. Our example that we're going to use is methane. You might recall this diagram from when we were talking about bond distances. We said that if the bonds are too close together, they're going to be high energy. And if they're too far apart, they're going to break. Down here you see the carbon-hydrogen bond. That's where the bond is partially broken, and this is where the bond is fully broken. This energy that's associated with the bond breaking is called the bond dissociation energy. We're going to look at the kilocalories per mole. You can see here that it is 105 kilocalories per mole in order to break this carbon-hydrogen bond in methane. Here are some bond dissociation energies. You can see that I've pulled a couple of examples from your book. I've also added a couple of examples that are not listed in your book, and you can refer to this chart or you can look at the ones in your book or online. I've listed the values in kilocalories per mole, and you can see that these values are at 298 K. If we think about the example we just looked at, here's a carbon-hydrogen bond for methane at 105 kilocalories per mole. And if we go back to our diagram, you can see that our bond energy is 105 kilocalories per mole. It's important to note that the carbon-hydrogen bond dissociation energy for ethane is different than for methane. The bond dissociation energy also differs from ethyl to isopropyl to T-butyl. And we're going to refer back to this chart periodically during this lecture. When we look at the major products of homolysis or homolytic cleavage, we often see that the weakest bonds in the molecules are the ones that are going to break. So in this case, we see that a carbon-bromine bond is breaking. Let's go back to the previous table and look at the bond dissociation energy for a carbon-bromine bond as opposed to a carbon-hydrogen bond. The carbon-hydrogen bond is here at 105, and the carbon-bromine bond is here at 70. So 70 kilocalories per mole is the smaller bond dissociation energy. That means that the carbon-bromine bond is the weakest bond, and given a little bit of light, it's abbreviated HV here, that bond is going to break and form two radicals. And if you want to add in your arrows for homolysis, remember that they would be single-barbed arrows, and we would show one arrow going to the bromine and one arrow going to the carbon. Now let's talk a little bit about the common elementary mechanistic steps that radicals undergo. You can see here that we have radical coupling, which is two radicals coming together. We're also going to talk about bimolecular homolytic substitution, where we have a radical replacing another radical. And we're going to talk about radical addition to an alkene or an alkyne. A radical coupling reaction is shown here, we can see one radical. In this case, we have a hydrogen radical reacting with a methyl radical. And those two radicals are coming together to form a carbon-hydrogen bond. So this blue radical becomes half of the carbon-hydrogen bond, and the red radical becomes the other half of the carbon-hydrogen bond. So we're going from two radicals to a formation of a covalent bond. In bimolecular homolytic substitution mechanisms, you can see that we're going from a radical to a new radical. In this type of reaction, we're reacting a radical species with a non-radical species and getting a new non-radical species and radical species. In this case, the red methyl electron becomes part of that carbon-chlorine bond. The chlorine-chlorine bond here involves two electrons, one which forms the other half of the carbon-chlorine bond, and the other half which forms a radical on the chlorine. So we have red electron and blue electron coming together to form the carbon-chlorine covalent bond, and the green electron, the other half of that chlorine-chlorine bond there, becoming a radical on the chlorine. Here's another example of a bimolecular homolytic substitution, or an SH2 reaction. And in this case, our radical is coming from a bromine. The bromine radical becomes half of the hydrogen-bromine bond. The other half of that hydrogen-bromine bond comes from the carbon-hydrogen bond. And the radical on the carbon comes from the carbon-hydrogen bond. This particular type of SH2 reaction is also referred to as a hydrogen atom abstraction because we are abstracting a hydrogen from a non-radical species. The hydrogen in this case becomes part of the HBr shown over here on the right. Our last mechanistic step is radical addition to an alkene or an alkyne. In this case, we have an alkene that is reacting with a bromine radical. Bromine radical over here becomes half of the bromine carbon bond. The other half of that bromine carbon bond comes from one of the pi electrons. And the other half of that pi bond becomes the radical shown. So that pi bond breaks, one electron going to the carbon and the other electron going to form that carbon-bromine bond. And that bromine radical also becomes part of that carbon-bromine bond. This can also occur with alkynes. In this case, we have sulfur radical reacting with a pi bond. So that sulfur radical becomes half of the carbon-sulfur bond. The other half of the carbon-sulfur bond comes from an electron from the pi bond. That other electron in that pi bond becomes that radical on the carbon there.